Hi, today we're going to be talking about resonance structures. Now we've seen before, when there are two adjacent atoms that have p orbitals, they can form a bond. And what resonance structures help us do is understand the flow of electrons when there is more than just simply a double bond. So for example, again we can highlight this double bond as the component being blue, highlighted in blue, to represent that these are the p orbitals that are in play. Now, what happens when there is a third p orbital, now adjacent to these existing p orbitals? This third p orbital will be on this carbon over here to the right, but there's no clear way that it's going to be interacting with the other orbitals, at least based on this drawing here. But in reality, all three of these p orbitals are in a continuous kind of circuit of a p orbital, a highway for electrons. So keep in mind that this orbital here, this line, implies that there are two electrons in that bond. And now, how many electrons are in this other p orbital on this third carbon? And there could be either 0, 1, or 2 electrons. So in the case when there are 0 electrons, that gives that carbon a formal positive charge. And you can go back to formal charges if you want to work on how that is the case. So if there's a formal positive charge there, the electrons can be shared from the orbital to the left, and you can also draw a structure where these electrons are residing between these two carbons on the right. And you might say, well, you've just flipped the mirror image, but in fact you can keep track of which carbons are which. When we do this is called a resonance structure, and this is a resonance arrow. It's a very special arrow. It has two heads on a single line that is only to be used for resonance structures. It's called a resonance arrow. And so again, if you highlight one of these carbons, so in this structure on the left, it looks like it has a double bond to the central carbon, and on the structure on the right, it looks like it has a carbocation. In reality, the truth is somewhere in between. It's being shared across both of those two carbon atoms. So if we look at a system where there are two electrons on that carbon that didn't have the double bond on it, you have an anionic charge, a negative charge, so it's a carbanion. And similarly, you can move those electrons. Now keep in mind that we can't push the electrons from this double bond onto this carbon, onto the space between these two carbons, that is forming another double bond, because there will be too many electrons on this carbon here. You would have a super valency. And so instead, we have to push electrons from the negative charge, and you always want to make very clear, concise arrows where you go from the atom where it's going to, and in this case you're going to form a new double bond, so you draw between the two atoms here. But we can't stop there. So if we stopped there, you'd have a structure like this, which at first pass you might say doesn't look bad. It looks like all the carbon atoms have 4 bonds to them, but in reality there's this proton on this central carbon, and it's been there all along. You really have to keep track of those protons, protons or hydrogen atoms, and this would be hypervalent, meaning it has too many bonds to it. 5 bonds to carbon is bad. It's not acceptable under most circumstances, and certainly in this class it's unacceptable. And so what we do is we have to continue pushing this electron density all the way on to the terminal carbon. So we go from this bond to the terminal carbon, and again we draw a resonance arrow. And as I mentioned before, both of these structures, in reality, it's not that the negative charge is on the right or on the left, but it is truly found in both locations. And so sometimes you'll see a representation like this, where you see a cloud of electron density. You can really think about it like a cloud or a marshmallow, a puffy cloud of electron density being shared across those 3 atoms. So in this system, you have 3 atoms and 4 electrons being shared across those 3 atoms. In this system up here, you have 3 atoms, 3 carbon atoms, and you have 2 electrons being shared across those 3 atoms. So let's look at some do's and don'ts for resonance structures. The first do is look for pi bonds, and there have to be pi bonds and p orbitals in order to have resonance structures. A second do is to use your resonance arrows. That's a really important feature two resonance structures when you're trying to convey information to other chemists, to use proper resonance arrows. And the third is to always make sure that you are maintaining the net charge. If somehow you've either destroyed or created a net charge, then you can tell that you've done something incorrect in your resonance structures. So let's look at some don'ts. Don't move sigma bonds. So in resonance structures, we're simply moving the electrons along the p orbitals. We're not actually moving any of the atoms. So that's one of the key features of resonance structures. None of the atoms are actually moving their position. This is a time average view of where the electron density is at any given time. You don't want to take electrons away from nitrogen or oxygen. We'll see some examples in the next slide of what it looks like to do some proper resonance structures. So nitrogen and oxygen, you never want to have an incomplete octet on them. You don't want to have them have 6 electrons, be hypovalent. One way to remember that, a very simple rule, is that nitrogen and oxygen say NO, no. All right, so now if we look to practicing resonance structures, here are some common structures that are often asked of you on exams or quizzes. And these types of structures are also often found on more complex structures. So look around for complex structures to see where there are bits where resonance is at play. So the first step is, of course, to draw our resonance arrows. Don't forget the resonance arrows. The second, I highly recommend drawing in your lone pairs of electrons. It'll make sure you're keeping track of how many electrons. So you see that this oxygen has a full octet, has 8 electrons. This oxygen also has a full octet. And you see these electrons are going from this oxygen to a double bond, and you might think, hey, you just said you can't give electrons away from the oxygen. What that would look like is if you were to take a carbonyl, I'll draw it right here, and take electrons away like this. So this resonance structure, I'm about to draw it, but I don't want to ever see you draw it, is bad. So this would create a situation where you have 2 electrons on the carbon, and only 1, 2, 3, 4, and then the double bond makes 6 electrons, or the single bond makes 6 electrons on oxygen. So this would give oxygen a formal positive charge, carbon a formal negative charge, and those charges in their own right aren't bad. The key thing here is that oxygen has only 6 electrons, 6 valence electrons, and that's unacceptable. So again, I'm actually going to just get rid of that structure because I don't want you to see it and think it's acceptable. I'm going to go ahead and cut it away from the screen. Okay, so going back to this up here, you're moving electrons, you're going to bounce the electrons. When you have a 3-atom system, you often see this little bounce kind of electron density, and you wind up with a structure shown in the top right. So if you have this imidazole structure with nitrogen atoms, again, the first step I recommend doing is drawing the lone pairs of electrons on these atoms. And again, you have a 3-atom system, and you're bouncing the electron density from one side to the other. And note, in this first case, you maintained the net negative charge, we're good. Here you have a neutral molecule, and it might seem at first pass that you've broken a rule here, but if you recognize there's a negative charge and a positive charge, the net charge of the molecule is still neutral. This is an acceptable structure. I'd like you to practice some other structures on your own. You can check with me and see how you've done. This third system is now a even longer pi system. So you have these 3 atoms here where you can draw a resonance structure, and now you have this carbocation in the middle, and you can draw another resonance structure as well, and I'd encourage you to practice that one. The final compound here is an amide at the bottom left, and this is an incredibly important molecule, or incredibly important functional group in the context of proteins. And it's really this resonance structure that helps us to understand some of the reactivity and the shape of proteins. So again, we draw in our lone pairs of electrons, so with nitrogen having 2 electrons, and it's a 3-atom system, so we push the electron density up onto this oxygen. This gives nitrogen a formal positive charge and oxygen a formal negative charge, and now again we have still a net neutral molecule. But what this does is it tells us that we have some double bond character between this nitrogen and this carbon, which means that the rotation around that bond is going to be hindered a little bit. It's going to be a little bit more rigid than if it was simply a single bond. And that's just kind of a teaser into the biochemistry portion of organic chemistry. Thank you for your time. I'll see you next class.